This is Chapter 13, Section 1, and it's on climate. The objectives today are to explain the difference between weather and climate, to identify 4 factors that determine climate, explain why different parts of the Earth have different climates, and to explain what causes the seasons. So when you wake up and you ask what is the weather, you're thinking about one specific day. When you ask what is the weather, you're not asking what is the weather over a year time period. You're asking for a specific day, and that is the difference between weather and climate. Is weather is talking about a specific day, whereas climate is the average of those days. It's the average of the weather conditions in an area over a long period of time. And there's a variety of factors that are going to determine climate. Some of the big ones, or rather the biggest one, is going to be latitude, which is the distance from the equator. It's going to be global air circulation patterns, oceanic circulation patterns, topography, so how high up you are, solar activity, and volcanic activity. In latitude, we measure it in degrees, where right at the equator, you're going to be at 0 degrees latitude, and then the most northerly and the most southerly are going to be 90 degrees north and 90 degrees south, which are the north and south poles, respectively. And the reason why latitude is going to be the strongest indicator of climate is because where you're at latitude-wise determines how much sunlight you receive. Where the equator is going to receive the most direct sunlight, whereas the further you move up in latitude, you're going to begin to receive sunlight that's slightly off. I'll show you a picture here in the coming slides where it kind of shows how the sun's light, the rays of the sunlight spread out as you go increase in latitude. So right here, where you have the equator right here, this little belt around the Earth, and these get the vertical rays from the sun. So these right here, this is going to get the most direct sunlight. Think of like whenever you read directly underneath a lamp versus when you receive the oblique rays from the lamp, meaning where you're kind of sitting in a chair that's further away, maybe like, 10 feet away from the lamp. That's kind of how you can think about the sun's rays as you increase in latitude. Whenever you're near the equator, you're going to have days that are right about even, 12 hours at night and 12 hours during the day. And you're always going to have temperatures that are high year-round. There's not going to be any summer or winter. It's going to be pretty much consistent with your climate. However, when you get to higher latitudes, that's when you start getting some variations in the time of how long night and day are depending on the time of the year, and what temperature it's going to be depending on the time of the year. And again, that all has to do with how the angle that the sunlight's going to start hitting the Earth. So you're going to have more of a variance in temperature as you increase in latitude. So meaning you could have at 45 degrees north, you could have about 16 hours of daylight, or you could have as little as 8 hours of daylight, depending on 16 hours during the summer and then only 8 hours during the winter. Whereas when you're all the way at 90 degrees latitude over by the north and south pole, the sun, you have the most variation in temperature and the amount of sunlight. The sun could set for only a few hours, where you have like 20-something hours of daylight, or the sun can only be up for just a couple hours. It just depends. And there's 3 important properties of how air, of air, that's going to kind of illustrate how air circulation affects climate. And these 3 principles here are kind of the important things to keep in mind, because global air circulation, as you'll kind of see in the coming slides, it can kind of get into a lot of specific details that, don't get lost in the details, but kind of focus on these 3 main ideas. These are kind of the takeaway points. The first is that cold air is going to sink because it is denser than warm air. So the basic idea here is anything that's colder it has more particles clumped together. Versus something that's warmer, if you just think of basic chemistry, particles that are warmer, that have more energy, they're moving around more. Whereas particles that have less energy, they're moving around less. So there's more density. Remember, density is how much of something is in a certain area. So colder air is going to be more dense, so it's going to sink, and warmer air is going to be less dense, and so it's going to rise. Meaning that the warm air is going to rise, the cold air sinks. However, as the cold air sinks, it's going to begin to warm up. And so you can kind of imagine, the warm air gets pushed up, and the cold air, because it's more dense, it comes down. But as that cold air comes down, it's going to receive more, it's going to warm up because it's going to begin to receive the heat that's coming from the earth, whether it's from the land or from the ocean. And the heat from the land or the ocean comes from the sun, which creates warm air again, and then you kind of start the cycle over again. And as this warm air rises, this warm air is going to cool down, and then it turns into cold air, and then just on and on and on. And this, again, it's just a cycle. And so you can imagine that this, forms a circulation pattern. The final thing is that as warm air rises, it has more space between all these particles, and that space allows it to hold more water vapor. However, as this warm air that's holding more water vapor rises and it begins to cool, that water vapor is going to condense into liquid water that's going to form either rain, snow, or fog, and you're going to get more rain. So that's why over in the equator you get more rain, because this air circulation pattern is kind of in overdrive, right? Because this whole thing is kind of driven by the sun, right? Because the sun is heating up the land or the ocean, which causes the air to warm up. Air warms up, it can draw more water vapor, and then as that warm air rises and cools down, that water vapor condenses into liquid water, and it's basically the water cycle. And so this pattern, of air rising and falling based on pressure, that's called wind. That's what, whenever we feel wind, that's really what we're feeling, is this movement of warm air up and cold air down. And again, because different areas of the earth receive different amounts of sunlight, and because the earth rotates, one time during the day, and different latitudes are going to receive different amounts of that solar energy, this whole pattern, this whole cycle, that I just drew, is going to vary. It's going to vary depending on where you're at on the earth and during which time of day and time of year you're at. And this circulation pattern is related to the precipitation pattern. So everything is connected here. And this is a graph that's kind of explaining what I just went over. So, if we start here at the equator where you get the most direct sunlight, you have your warm air. This warm air is sucking up all that water vapor, and then it turns into your cold air, and as it sinks down, it's going to release some of that water vapor. That water vapor is condensed into liquid water, and it's going to fall down like rain. Okay, so I'll keep moving on. Okay, we already talked about this. Whenever you're at the equator, we talked about the hot air. The air gets hot because you have so much direct sunlight occurring at the equator. Well, normally the cold air wants to come back down. You think about that cycle. However, because you have such a continuous supply of warm air, this cold air isn't going to sink immediately. Rather, it's going to keep being pushed until you reach, if I go back to this slide, because you have this, your cold air right here, because you keep having this continuous supply of warm air, this cold air can never fall back down. and it starts to fall back down, but it only happens right here at 30 degrees north and 30 degrees south latitude. And the result of that is, as that cold air comes back down, it's going to start to warm up. That warm air is going to start sucking up the water vapor from the land below, which is going to create dry conditions. So that's why a lot of your deserts are going to occur at 30 degrees north and 30 degrees south latitude, because that cold air that warms up sucks up all that water vapor that's in the air down below. Okay. Um, so you have air descending at 30 degrees north and 30 degrees south latitude, and that's going to move towards the equator. And air moving toward the equator warms while it's near the Earth's surface. Then at about 60 degrees north and 60 degrees south latitudes, this air is going to collide with cold air traveling from the poles. Then the warm air rises, and most of this is uplifted air, is forced towards the poles, where cold, dry air descends at the poles, which makes them very cold deserts. Essentially, the main idea here is that you just kind of have these cycles going on, where you have a repeat in this cycle right up here at the poles, where you begin to have another kind of desert-like condition like you had here at 30 degrees north. The basic idea here is that, it's a cycle. And that cycle, kind of all this together, influences weather. And you can imagine that it's kind of complicated to some degree, right? There's a lot of arrows going on here. And so that's kind of why the weatherman or weatherwoman's going to get this wrong sometimes. Okay, just some more terminology. A wind that's going to blow predominantly in one direction throughout the year is going to be called a prevailing wind. And because of the rotation of the Earth, these winds are going to blow northward or southward. Or excuse me, not going to point directly northward or directly southward. Rather, they're going to be deflected to the right in the northern hemisphere, and then to the south in the southern hemisphere. So you can kind of think of this, like imagine I had a little circle here, and I started rotating this circle. You start rotating the circle. As it's rotating, you start trying to draw a line. And if this circle wasn't rotating, the line would go straight out. But as you're rotating the circle, all of a sudden my line's going to start curving because the circle that I'm drawing on is rotating. And that's the same idea here with the prevailing winds, which is why they're going to have this slight curving going on. Most of these are belts of prevailing winds that are going to be produced between 30 degrees north and south latitude in the equator are going to be called the trade winds. And the trade winds are going to blow from the northeast in the northern hemisphere, and then from the southeast in the southern hemisphere. And these are the trade winds right here. And then you have the westerlies and the easterlies. The westerlies are produced between 30 and 60 degrees north latitude and south latitude. And when you're in the northern hemisphere, the westerlies are a southwest wind, and in the southern hemisphere, they're going to be a northwest wind. And then the polar easterlies are going to blow from the poles to the 60 degrees north and south latitude. So the movement of the ocean currents are going to have a great effect on the climate because water holds a large amount of heat. As I mentioned, thinking back to this kind of circulation of air, this warm air is able to absorb so much heat, or rather, as this cold air drops and it warms back up because water holds so much heat. Well, largely because water holds so much heat. So imagine cold air coming down over an ocean. That cold air is going to warm up pretty readily because that ocean holds so much heat in it. Whereas if water didn't hold as much heat, you're not going to be able to heat up that air as much. If you're not heating up that air as much, you're not going to get as much water vapor, which means you're not going to get as much rainfall. How these ocean currents moved is going to be caused largely by your winds and by the rotation of Earth. And these surface currents are also going to redistribute the warm and cool masses of water around the world, which is going to, alter the climate in different parts of the world. One of these movements of water is going to be known as the El Nino. So El Nino and La Nina, they're opposites of each other, and they occur every 2 to 7 years. And basically, what they are is you have it's a pretty simple idea, and it's just that over in the Eastern Pacific Ocean, you have for El Nino, you have the surface water temperature becoming unusually warm. And what happens from this is that the winds in the Western Pacific Ocean, which normally are weak, are going to strengthen and push that warm water eastward. And the result of this is that the rainfall is going to follow this warm water, and it's going to produce increased rainfall in the southern half of the U.S. But then it's also going to cause drought in Australia. And then again, La Nina is just the opposite of that, where you get a cool phase that occurs. Another oscillation of currents is called the Pacific Decadal Oscillation, which is a long-term, about 20 to 30 years. It's gonna flip-flop where you get a change in the location of warm and cold water masses in the Pacific Ocean. So the PDO is going to influence the climate in the Northern Pacific and in North America. So topography, how high you are above sea level, is going to influence your climate, which I think is kind of intuitive to some people. As you go up a mountain, you think of if you're climbing Mount Everest, what people wear when they climb Mount Everest. They're wearing, warmer gear. They got more jackets on and stuff. Temperature typically is going to fall about 6 degrees Celsius or 11 degrees Fahrenheit for every 1,000 meters that you increase in elevation. And a mountain range is going to influence rainfall patterns. So we have an ocean here. And again, oceans hold a lot of heat. So that heat from the ocean is going to warm this air. The warming of the air is going to draw with it the water vapor from the ocean. This warm, moist air that has a lot of water vapor is going to go up over the mountain, and as warm air travels up, it's going to start to cool down. As the air cools down, that water vapor is going to condense into this liquid water in a cloud, which is going to lead to rain. However, it's going to release all of the rain on this side of the mountain, so that by the time the air reaches all the way up here, it's cooled down. And as that air cools down, it then starts to descend the mountain. As it goes down the mountain, it's going to start to absorb all this heat from the land below, and it's going to warm up. As it warms up, as the air warms up, it then begins to start to suck all of the water down below here up into the clouds with it, resulting in a kind of a desert-like condition here. So you kind of get feast or famine with mountain ranges, where you have an area of large amounts of rain and then a desert area. So this is a perfect example of the weather in California, where over here, you got a nice amount of rain, it's really green and lush, but then you cross over the mountain range and you're over, like Nevada or something, right, where you have the deserts. So some other influences on Earth's climate are going to be the sun, specifically what's called a solar maximum. And a solar maximum is going to be when the sun emits an increased amount of UV radiation. To remind you, UV radiation is the radiation that we don't want. UV radiation is going to produce more ozone, which is going to warm the stratosphere. And some of that radiation will also get to the lower atmosphere. We're going to warm the surface of the Earth as well. And then a volcanic eruption is going to release a lot of sulfur dioxide. And this sulfur dioxide which can remain for about 3 years, is going to react with some water vapor and dust in the stratosphere, the upper part of the atmosphere, and that's going to form this haze. And this haze is going to block out the sunlight, or rather, it's going to reflect the sunlight, and it's going to cause global temperature to decrease. Basically, the haze blocks the sunlight from getting to the Earth, which is going to decrease the global temperature. The final thing to consider is seasonal changes to the climate. So seasons come about because the Earth has a tilt. The Earth isn't straight up and down, but rather it has a tilt to it. Think of like a globe that you would see in a classroom, and it has a slight tilting to it, which you see here. Because of this tilt, different times of the year you're gonna receive different amounts of sunlight. So this is for the northern hemisphere, where here in the summer, for the northern hemisphere, you're getting, northern hemisphere being the upper part from the equator, you get more direct sunlight. Whereas in the southern hemisphere, it's the opposite. It's winter there. Contrast that with the winter for the northern hemisphere. It's being pointed away from the sun, so it gets less direct sunlight. Whereas in the southern hemisphere, it's flip-flopped. For them, it's going to be summer when it's winter for us. And that's saying everything that I just said there. Okay, that's going to do it for this section.